to the website of the school, there should be, in the hands-on session part, there should be 2 files somewhere called hands-on session 1, and there are instructions 1, instructions 2. And if you open these, you should get 2 PDF files, and they are each, some lengthy write-up. And you can take a look now at this. And I tell you in words what this describes. The first one here is called hands-on set 1. Here the idea is to learn and run a little dark matter simulation with the gadget code and body code, and also before that setting up initial conditions with an initial conditions code. So cosmological initial conditions, running a simulation, running a group finder, and then there are a bunch of questions on analyzing this simulation, which will get quite involved. So this we can't do now this afternoon. This is just more for the fun of you. At your leisure, you can think about these questions. And this is basically hands-on set 1. The other one is some very simple hydrodynamical simulation carried out with the Athena mesh code. Athena is from Jim Stone, a nice mesh code. And there we would simulate a Kelvin-Helmholtz instability and a Taylor blast wave. And my question is now, which of these problems we would like to do together now? My preference lies on the hydro side. So let's make a poll. Who wants to do the problem 1 now? Okay. A few people. Who wants to do the problem 2? Okay, these are more narrowly. So, well, I haven't talked yet about hydrodynamics, so we need to get basically fast forward a bit. But with a leap of faith, and the instructions I think are explicit enough, we can do this. So take a look at this. Maybe you read this a little bit. So what we'd like to do here is to simulate a Kelvin-Helmholtz instability with the Athena code. And the text here specifies the initial conditions that we're supposed to set up in a squared box with periodic boundaries on the left and right sides. We have a top half and a bottom half. It basically means we set something up at pressure equilibrium to have a pen somewhere. Basically what we want to have is a box of size L. And then we split this in 2 halves, and then one of the fluids is moving to the right, and the other one is moving to the left. Whatever let's call this V2, V1. And we have a density ρ1, ρ2, and some temperature U1, U2. And these two combinations of density and thermal energy per unit mass will give you a pressure, and that should be the same on both sides. So we are setting something up at pressure equilibrium and nice subsonically. So that will be the setup, that we have a gas streaming past an interface. And the density profile will make this a little bit washed out here, so that it's not overly sharp, the density profile. This is explained in the text. And then we would like to perturb this velocity field slightly. We add some little perturbation in the y direction. So some velocity maybe like this in the y direction. And this is just to make one particular mode grow faster than the others. Yeah, that's sort of the idea. And then we expect, and I will talk a little more about this when we discuss fluid instabilities, that this flow is unstable and will create so-called Kelvin-Helmholtz billows. Right, so then I guess we can jump into the action in actually setting this up. So the Athena code is written by Jim Stone and colleagues in Princeton. It's a very nice MHD code. nice piece of, I'm using it here because it's fairly easy to get started with it, especially because you can actually program the initial conditions in this code directly in the code. And that is what we have to do also. And it's more or less described here. So let's see. You are free to start working on this. I'm also trying to do this now here, following the instructions. And we see how far we get. And this is not a race, okay? So we anyway, I have to delete every second character I type because I'm constantly mistyping. First of all, we need to get the code. So I've already downloaded Athena, so I have here a directory with the Athena code. First thing you do is unpack it.
Is it possible to make it a little bigger?
You mean my window?
Yeah.
Okay, sure. How do I do this? I'm fairly primitive in my techniques, you know. Should be possible to enlarge the font. Let's see. Plus. Yes. Is this better? Okay. Yeah, so what I've just done, I've just unpacked the code, right? Now, what Athena creates itself a directory, which we see here, Athena 4.1. And in this directory is the source code hidden in a subdirectory, documentation, etc. And then this code is using a configure script where you have to enable certain options. For example, what hydrosolver you want to use, and what in particular also what problem you want to calculate. So this code has the notion of problem generator. So there is in the source code directory, there's a directory called prop, where various problem generators are stored, and we don't have, so these are things that you can in principle use and modify. And what we now use is one that I actually prepared here in the write-up. There is somewhere, yeah, it says here, here, this line, oops. Yeah, so if I click on this, it has already downloaded it. Here is, here, if you read all of the text, where is it? Just saw it here, yes. Here somewhere in the text, where it says HTTP, www, MPA Garden, yada yada, there is a file kelvin.c, which is simple problem generator that I prepared for this exercise. So I downloaded this here. Now I will save that. I'll save this file. You can also use wget for this. I need to save this in the problem generator directory of Athena. So where was I again? Talks. Okay, there we are, Athena, source, and then prop. Okay, I saved this there. Okay, so far so good. Now we have a problem generator, and in this problem generator we need to program the initial conditions. And these initial conditions are described here in the LaTeX text file. And we can try to do this together now. So I have here my kelvin.c. And fortunately, the screen is really small now here on the projector. So if you scroll through this file kelvin.c, I mean, there's a function, a C function called problem that is in Athena language is setting up the problem. And Athena has also an ASCII parameter file, which is a separate thing we later have to do. And in this ASCII parameter file, you can also define your own additional parameters. And they can be parsed here with this function parameter get double precision value or something like this, probably thing. And this is from the section problem. It tries to get the parameter describing density 1 and density 2, Vx1, Vx2, pressure and amplitude. So these are things we'll specify in the parameter file in ASCII. And our problem generator should read that from the parameter file. And then what this problem generator does is actually doing one loop over the whole mesh. And this is this for loop here, going over the sort of in a Fortran style over the z coordinate first. Not sorry, over the c first, which is unusual to see, but then y and then x. So the I, j, k are the integer triples that index a mesh cell. And in this hydrodynamical mesh code, you have to specify the initial state of the gas for all of these cells. And this is how Athena does that. So here, this function gets you the spatial coordinates x1, x2, x3 of cell I, j, k. So this is what we can use to exploit in setting up our density field. So what I actually put in here, dot, dot, dot. So we need to calculate the density of the cell and the velocities of the gas. Okay, this is what I've marked here now between these two red lines with the 3 dots. This is what you have to fill out, each of you yourself. And now I have to remember what the formula is. This one, so row 1. So we need to put in here what is the density 1. This is called dense 1. So dense 1 plus dense 2 minus dense 1. And then there was a division by 1 plus some exponential, I think. What was this again? So this is just a smooth transition in the vertical direction from the density 1 to the density 2. So we take here y minus, this is now hard-coded, slightly ugly, the central line of the box. We use a unit box, and we divide this here by 0.01, say. So is this now the right formula that I typed in? I think so. Sigma, what do we want here? Stated 0.01, right? So, you know, this is a nasty style, quick and dirty programming, but never mind. So we have some hard-coded parameters here. So that's the density. Now we need the velocity in the x direction. That's the what this formula 2 describes. And we have to check what the velocity is. This is the Vx1. We basically use a similar formula, Vx1 plus. We go from the one velocity to the other in a smooth way. And y minus 0.5. So this is now, of course, yes? Yes, it's x2. Thank you. Normally, I only learn this by the compiler, but this is true, x2. This will be our y coordinate. That looks better, okay? And then the y velocity, what was that? Yeah, this is now our perturbation. Okay, there's perturbation amplitude A, that we called here amplitude. Then we modulate this via our wave. This is k wave times the x1, that's the x coordinate, times, again, an exponential. What was this? minus k. So now big question, what is wrong here? V1. Okay. This one, you mean? Okay. Other mistakes here? I still see one.
Yeah, the exponential should be k wave.
The k wave, yeah, and I see still another one. It's amazing how many things you can go wrong, right? Now I see a mistake that will not be flagged by the compiler, which makes it particularly nasty. Yeah, this absolute function here, you know, it returns an integer. Oops. This needs to be fabs in C, right? This is a really, really nasty one. And it will make a difference, believe me. Okay, so now what you see, we calculate these things, and then what you need to initialize is in this grid structure is the conserved quantities. No, sorry, actually the primitive quantities is the density. This is the speed, this is the momentum density, and that's the energy density. So here Athena uses capital E, but it's energy density. Okay. Here is the thermal energy density plus the kinetic energy density. Then, okay, now we can save this thing, and we can proceed to compiling the code. And the compilation, for compiling, you need to configure Athena. This is this configure statement. So here you have to tell the code what options are supposed to be used. And for this, you go back to the source, to the main directory, and you then, it's already started, sorry, it chopped off something. Ooh. Yeah, with row flux, yeah, we want to add also this. So we use here what this means. So this configure script, and we pass some parameters. We say with problem equal to Kelvin. So the problem generator we just wrote should be used for Athena. Then it uses hydrodynamics as opposed to maybe other choices, MHD, etc. Equation of state is adiabatic, means ideal gas equation of state. And the Riemann solver is the row solver here. Okay, then we compile we configure it. That has worked for me here. Then you make all. Then should compile in principle. Yeah, so it worked for me. Thanks for your help getting all the syntax errors sorted out. So now I've compiled the Athena code, and okay, I'm ready to run in principle. The executable is here, has appeared in the bin directory. So if I start bin/Athena, I start the code, and I get a fatal error. Parameter file is missing, right? So this code uses also an additional parameter file where you have flexible options. And so we need to create this parameter file now. And guess what? I prepared one. Here is a simple parameter file, which I now save. Fuck, getting wrong. I now save that to the Athena directory. Okay, now it strangely renamed this to kelvinparam.txt. That's what Chrome did. I Where is this? Call this again Kelvin.perm. Okay, now let's look at this parameter file. This has in Athena this sort of format. The code distinguishes here between different sections, comments, job description, output, different output files, etc. This is something that is more or less in okay settings here. We'll get some picture outputs also, and output section 3. What is most of this here is annotated and relatively clear. We would like to run with a Kurov factor of 0.4 up to time equal to 3. And what's now interesting is these sections that describe the domain. nx1 is the number of mesh points in the x direction, and nx2 is the number of mesh points in the y direction. And then you have also dimension here, x min and x max gives the dimension. Yeah, let's go for low resolution here, 128. This is not so low ultimately, but I think it's enough for first trial. 64 would be even faster. Let's do this, 128, or I do this now here. And okay, gamma and the pressure you can set, and then what we see here, the density contrast is 1, is a factor of 2, 1, 2. The amplitude of perturbation is 0.05. Now there's one thing that when you read carefully, there's one difference between the x and the y direction. If you look here at this section, this is the from this line to this line. This describes basically the grid in the x direction, and this describes the grid in the y direction. What's the difference? Boundary conditions, yes. So here are different flags set for the boundary conditions. So the 4 on the left and right side would mean periodic boundaries. And in the text, it was stated we would like periodic boundaries now. So we should better change this here also. Okay. Other than that, looks kind of okayish. So I can save this. And now I'm in the position to maybe try whether it runs. I have to pass to Athena this parameter file with the -I flag include the Kelvin parameter file. Okay, and now code runs and cycles through the calculation here. And now we have here at time 1, we ask it to go to time equal to 3. Okay, so I'm done. And that's the output. So as basically when you look at the parameter file, you'll see that there are different outputs were requested. A tabular output at a certain interval. These are the .tab files. These are ASCII files that describe describe the state of the simulation, and there are these PPM files. This is a simple image format, and we could, for example, look at, say, the initial state. This would be this time equal to 0, and then I have here in the top left now an image, which is should be the initial conditions here, basically. Okay, and this shows some color map overlaid over our density field. Now that's really good that I have so poor resolution, because that gives me a bigger thing. If you have a retina display, you probably will not see this thing almost. Very small. But now let's look at the final time. This was the output number 60. Ah, there you go. So, you know, it has changed. Kind of nice. Now, we would like, obviously would like to see this animated, so we can use image magic. Say, let's animate this stuff. And there we go. So here, I just now display all of these images one after the other. Of course, you can make an animated GIF or a movie out of this, and do this at higher resolution also. Okay. Are there any questions about this so far? Okay, so maybe I let you play with this a bit more, and I go to the restroom.
Oh, this is the image magic package that has that. Yeah, it has this command convert, which you can
that has that.
I don't have it installed on my laptop.
Yeah,
I
well,
have it on my desktop Mac.
do you have FFmpeg?
Yeah, but it doesn't work. I just typed in the command and it doesn't open in the QuickTime player. So perhaps in VLC. Maybe open
No,
it.
do you have I mean, have you made already a movie file? Yeah?
I use the command that's in the
Yeah.
notes to make the movie. Now I open it in QuickTime, it only shows
Oh.
black screen. So I don't know why. But,
Yeah, that
perhaps there's
is
something wrong
odd
with it.
for me. It should, yes?
No, it's very tricky.
Springel, I think this is probably the only program I've been having trouble with. When I try to run the test in the installation process, it says run test not found. I'm using Linux to do it.
Yeah.
So that might be-
What was not found? Sorry, I didn't get
So
it.
it says run test not found.
Can you
So
show
you-
me, maybe?
I'll check my laptop. So in the beginning part when you're configuring,
In the
it's
configure,
yes.
yes.
So in the configure part, you make and then you make you
Yes.
configure, you make all, and then you make test.
Yes.
So those are the three things that you do.
I
get
make
the
make
first,
make all. I make
all, and
make
then-
test. You don't need to make.
So you don't need to do it.
No, just make all.
So then it might be running. So I
Yes.
just haven't been able to try because then
Yes.
the laptop
So you don't
is
need
quite
to do
low.
actually make test.
Okay.
Okay. Maybe
so
if you so
even
make
if it
all is
says
enough.
It's
Yes.
not found. That isn't a serious issue. Then
No,
it's just literally for test
if
parameters.
make all doesn't give you an error, then it should work.
Okay.
Try this. Okay, maybe I just give you some short comments on the other types of problems that are described. In the exercise one was a little nasty test to calculate this thing in a boosted frame of reference when we add some constant velocity to everything. So we can see what happens then. So for this, I modify now my parameter file. No, sorry, my problem generator. Sorry. And I modify now the velocities and I boost them by some constant velocity 5. So I can say, for example, say 5.0 plus. This is giving all of the gas a supersonic, highly supersonic velocity, which will make it a lot harder for the code to follow it accurately, creating much larger truncation errors. So that is what we'll discuss more in the lectures. So if I do this, I go to a boosted frame, basically. If I keep running this now for a time of 3, then basically all of the gas would wrap 15 times through the periodic box and end up where it started. Okay. So if there was full Galilean invariance, the end result of this calculation would be the same as before. But now we will have, as you'll see, that's the sense of this exercise. You'll get some larger advection errors than before. And also the runtime will go up because we now need to do smaller time steps. So I change also my parameter file to create differently named outputs. I call this now boosted. And in principle, if I now redo the building of the code, I can run it again. And now it will run longer because of this boost. I'm draining my battery now. Okay, so this other calculation has finished, and I have now additional outputs for this boosted calculation. And as I said, in principle, physics-wise, we haven't really changed anything. It would now have wrapped 15 times through the box, and it should have arrived at its original place. And now let's see whether it's the case. And that's what you get. You know, it is. These two states look very similar, but one is a kind of a blurred version of the other. And here you see the large advection errors now that were created by the additional motion. And we'll discuss this more in the lecture, what this means. So. Are there any serious problems or questions to me about this?
Yes.
Yeah.
How can I plot PPM in the Mac?
How you can plot it in the Mac? Yeah, that's what I'm doing, because you have to have Image Magic installed, otherwise you're doomed, basically. Yeah, we can stop there and call it quits.
So I think we can close the session. We can warmly thank Volker for this nice hands-on session lecture. So the dinner will be at 15, 7:15, so in 15.